Hello, welcome. So, in the last lecture we discussed how to write down Navier-Stokes equations in simple Cartesian components, and then in case of a unidirectional flow how the equation gets simplified, and then we discussed the general boundary conditions that are to be implemented when a fluid comes in contact with a impermeable boundary. Okay. So, now we make use of these tools and then try to solve some problems. Typically, this is called exact solution of Navier-Stokes equations in books, but I mean you have to take it with a pinch of salt. Exact solutions for limited configurations, because the Navier-Stokes equations are highly nonlinear because of the inertial term u dot grad u. So, we will not be able to get exact solutions considering that term. Either you kill that term a priori with an assumption that inertial terms are neglected compared to viscous terms, okay, viscous forces, then you get some linearized equations. Alternately, you consider full Navier-Stokes equations, but bring in a particular geometry, and then the assumptions by virtue of the geometry you plug in into the system, then automatically the corresponding system gets simplified. So, these are the two approaches. Okay. So, maybe we will stick to the second approach that I mentioned, just to give you a feeling that we are really considering Navier-Stokes, but end of the day you will see, you will not see the complete nonlinear equations, because we are going ahead with the assumption that we are really getting exact solutions of Navier-Stokes. So, the simplest configuration which comes to our mind is, already if you see for unidirectional we have almost got the solution, because we got u as a linear function of the coordinate involving two arbitrary coefficients. So, we are almost through with that, except that we require two boundary conditions, right. So, anyway, not just that alone, we will add little more physics and then try to solve a particular problems. So, the first problem that we are going to consider is very popular in literature. Any elementary book on fluid mechanics would talk about this. Okay. So, that is flow between two parallel plates, right. So, you have two parallel plates and then flow driven by pressure gradient, or one of the plate is moving. Okay. So, that is the configuration. So, let us have a look at it. So, this is called plane quart flow. So, what is the configuration? You have seen x axis, y axis, and we are assuming that two plates are there at y equal to 0 and y equal to h, and the bottom plate is fixed, okay, and upper plate is moving. Since bottom plate is fixed, the velocity is 0, upper plate is moving, the velocity is given with the velocity of the plate. Okay. So, in literature this is quart flow, plane quart flow. Okay. So, what are the assumptions of the simplified equations? Flow is steady. So, that is the first assumption. Then flow is along x direction, which is nothing but unidirectional. Therefore, using equation of continuity, we have seen that u will be function of y. Okay. Then y momentum indicates that the pressure gradient along y is 0. Okay. So, that is a mistake. So, this is y is 0. So, the x momentum indicates that this is the equation. Okay. So, that is an assumption. Okay. So, this part is known. We are enforcing additional assumption, the pressure gradient is 0 and lower plate is stationary and the upper plate is moving. Okay. As such, from the y momentum we are getting dou p dou y is 0. So, dou p dou x is non-zero at that stage. We have got each equal to constant, right, but we are bringing an additional assumption that the pressure gradient is 0. So, then the question comes is, if the pressure gradient is 0, who is driving the flow, right. So, you have two parallel plates and you have only one momentum equation which involves pressure gradient and velocity, and we are killing the pressure gradient. So, then who drives the flow? So, one of the plates is driving the flow, right. So, that is the assumption. Lower plate is stationary and upper plate is moving. So, the flow is driven by the movement of the plate. Okay. So, that is purposeful. So, very simplified equation, okay, and it admits a solution linear. Then upper plate is moving with velocity v. So, therefore, you enforce this condition, and lower plate is at rest. So, therefore, you enforce this condition, then determine A and B. So, if we take this condition, B will be 0, simple, and if enforce this condition, then A will be V by h. Okay. So, that is what we get. The corresponding velocity profile is linear. So, which means you have two plates. Okay. So, this is x and y, this is at rest, therefore, u is 0. So, this is moving. Suppose these are the fluid particles, since the plate is moving with velocity v, what will happen? The velocity structure will be like this. Why we are visualizing this? This plate is stationary, this plate is moving. Okay. Since this is stationary, viscous effects are more here. So, the fluid adhering to this, they are at rest. Then the plate which is moving, that will drag the, because again here no slip, this is nothing but no slip, this is also no slip. The particles adhering to this surface, they move along with the velocity of the plate. So, therefore, the velocity is taken by these layers, but due to the viscous effects, they will drag slowly. So, as you are coming down, the velocity is expected to be reduced, then ultimately it should reach the no slip stationary. So, therefore, beyond a certain distance, you will expect such velocity profile. Okay. So, if you take such velocity profile is expected. So, it is a kind of shearing happening. Okay. So, that is the thing. So, this is a linear profile. Then volumetric flow. So, what is the volumetric flow rate? So, you take a small element, aerial element. Okay. So, then whatever flow with whatever velocity it is coming out, so that should be trapped within that area. Okay. So, if you keep on changing the velocity, naturally the total amount, okay, which is coming out of that varies, right. So, therefore, you integrate the velocity across that element. So, that is what we are doing. So, 0 to h, okay, means at a cross section we are, okay. So, this is distance between the plates 0 to h. So, that will be behaving like this. This is the total volume flux. Okay. Then shear stress at the upper wall. If you see the expression of shear stress, already it is written here. So, tau x y is mu dou u by dou y, that is shear stress, right. So, it is symmetric, tau x y is y x. So, here we are on a surface having normal along y direction, that is y equal to x. So, normally is along y direction, then x component we are. So, that is nothing but this. So, we have u and dou u by dou y is nothing but v by h, and therefore, this is the shear stress. So, you will not appreciate much what is happening here and all that, because it is very simple channel flow, it is a linear profile. So, there is not much of happening, except that the fluid velocity is taking the particles attached to the upper plate. So, they are dragged. So, you see a linear profile. Okay. Otherwise, the volume flow rate and the shearing effects, they are expected to be dependent on what are the other remaining variables involved. What are they? You increase the velocity. So, then what happens? More shearing happens. Then you increase the distance between the plates. Okay. So, correspondingly, the more volume will be trapped. Okay. Right. You increase the velocity or you increase the distance between the plates, the more volume flux is supposed to be accumulated. So, that is what is in agreement. Okay. So, you can plot and then visualize. Similarly, if you increase the distance, then the shearing effects are reduced, that is expected, right, because the impact of the movement of the plate will not reach the other plate. So, naturally if you keep on increasing, there is no shearing effect. So, that is an agreement. So, for a particular length, within a length you can add the corresponding measurement x we are talking about. So, it is like this. So far we are talking about only integration between 0 to h, but now within this length shearing, how much shearing is happening, okay, that quantification, this shearing happening, that quantification is given by this. So, naturally shearing is proportional to viscosity. So, that is what you get it. Okay. So, these are some important physical insights even with such a elementary problem. Okay. So, now let us slightly complicate, okay. Not complicating, we are adding another feature, you can say like that. Okay. So, what is the additional feature? So, we are now both plates are fixed, then the question comes, who is driving the flow? If you recall, we have killed the pressure gradient in the earlier case, right. So, now we have fixed the plates, therefore, somebody has to drive the flow, that means we are now anticipating pressure is driving the flow. Okay. I will not talk about this profile right away, okay. We will see this later on. So, this plate is fixed, this plate is fixed, located at y equal to 0, located at y equal to h. Therefore, we have stationary plates corresponds to no slip there, u equal to 0 and u equal to 0. Okay. Again same assumptions, instead of the earlier assumption of pressure gradient is 0, we are taking pressure gradient is constant. Okay. So, once pressure gradient is constant, this is constant, therefore, this has to be constant, okay, and both upper and lower plates are stationary, that is the assumption. Then we get a simplified equation which admits the corresponding solution. Still we have two arbitrary constants, right. So, go for the corresponding no slip boundary conditions, eliminate the constants. Only additional contribution is this time you have a dominating quadratic term which is not 0. You see, when I take y equal to 0 at y equal to 0 u 0, this constant goes off, but when you take u equal to 0 at y equal to h, this constant survives and this is very much there. So, the dominating part of this profile is quadratic, that means you expect a quadratic profile. Okay. So, this is the velocity and coefficients are determined and this is the parabolic profile. Okay. So, what is happening here? You have stationary plates, but the flow is driven by constant pressure gradient. Okay. So, then when this is stationary, viscous effects are more prevalent at these boundaries. Therefore, due to no slip, we expect some pressure is pushing from this side, but viscous effects are more prevalent. Since the plates are stationary, we expect the particles adhering to this should retain the velocity of the plates, but the pressure is driving the flow. So, beyond certain distance we expect this profile. Why? Because it is a symmetry, right. Now, you see the profile, that is what is happening, and this is very much satisfying. Y equal to 0, this is 0, y equal to h, this is 0. So, that is what exactly reflected in our profile. Okay. Now, magnitude, definitely magnitude depends on the magnitude of the pressure gradient. If you are having a large pressure gradient, then correspondingly the velocity is expected to be large or otherwise correspondingly low. And viscous effects, you have water in the channel, okay. Then you take some oil, you maintain the distance the same, you maintain the pressure gradient the same, it is natural that the velocities for oil will be much less than water. So, that is reflected in this solution. So, these are very elementary problems, but we can really nicely capture the corresponding physics. Okay. Now, we can compute the volumetric flow rate. Again using the similar arguments as we have given. Shear stress at the wall and the shear force within the length. Okay. So, this point I said we will discuss a little later. The maximum velocity occurs at the center line of the plate. From velocity you can compute the maximum occurs at the center line. So, why? So, this is what is happening, it is symmetric and both the plates are rest. So, maximum at the center line. Okay. So, the maximum velocity at the center line can be computed. It is varying over square of the distance between the plates, and it is always proportional to the pressure gradient. Okay. So, one can normalize. So, some people can define G by 8 as a new G. That means, we are normalizing the pressure gradient and simply call it it is some G h square by mu. So, there is no prefactor. So, that is also, these are some adjustments. Okay. So far we discussed very simple cases. So, we did not really appreciate how the Navier-Stokes equation gets reduced into such simple form, because it is unidirectional. So, left hand side is 0 and then y momentum is almost gone, etcetera, etcetera. Okay. Now, let us move on to a curvilinear coordinate system, say a very simple cylindrical system, then see how the Navier-Stokes equations really reduces under particular assumption. So, what is the next case that we are going to discuss? The flow between channel is called plane Poiseuille, and flow inside a pipe is called Hagen-Poiseuille flow. Okay. The assumptions are listed here. It is again unidirectional, but along z direction, and this is another assumption. What do you mean by axisymmetric? Okay. So, you take some surface, some object like this, then go for an axis. So, then can you call it this is axis of symmetry? Unfortunately, no symmetry. Okay. Whereas, you take like this, assuming I have drawn a nice picture. So, this is symmetric. Similarly, you take a cylinder, you have this is also symmetry, this is also symmetry axis. Okay. So, now when we define flow quantities which are independent of theta in cylindrical coordinate systems, so that means you have the corresponding rotations happening, okay, and they are invariant. So, the flow quantities are independent of theta, and whereas in spherical coordinates the flow quantities are invariant with respect to the azimuthal angle phi. So, then the corresponding flow is called axisymmetric. Okay. So, we assume flow is axisymmetric in this case. Okay. Now, very straightforward assumption, every time we are doing flow is steady, okay, then axisymmetric, that is independent of theta, then flow is unidirectional along z direction. Okay. So, here I would like to show you how the corresponding Navier-Stokes reduces slightly, okay, so that you get some idea. So, what I am trying to do is, we are considering cylindrical r theta z coordinate system, then we are writing r component. Okay. So, maybe we discuss maybe one or two components, not all. So, this is full Navier-Stokes I am writing in component form just to get an idea. So, the suffix indicates the component, not the partial derivatives. So, this is local derivative and this is the convective derivative and the corresponding pressure gradient, then the viscous term, so here you can appreciate the role of curvilinear coordinate system compared to the Cartesian. In the Cartesian, we simply could take the Laplacian on component u and component v. Here we can't do that, because the unit vectors, they are functionally depending on the coordinate system. So, therefore, we can't do that. So, one has to operate the Laplacian on the corresponding unit vectors. Okay. So, flow is along z direction, therefore, we must appreciate by writing the corresponding z component. So, theta we are not so much interested. In particular, the current case, our assumption is flow is axisymmetric. So, therefore, we are not so much focusing. Once we use these assumptions, you will realize immediately what will be the corresponding equation for theta component. So, this is the left hand side. Okay. So, we have considered two components, and please pay attention to our assumptions. Steady anyway, flow is axisymmetric, independent of theta and unidirectional. So, we are considering along z direction. Okay. Now, please come back. So, since it is steady, this is gone, and the major assumption is u bar is, this is our major assumption. So, what happens to r momentum? All are gone, then this is gone. So, all that we are getting is, we are getting this. Okay. Then here steady, this is gone. Since u z is non-zero, but there is u r. So, therefore, this term is gone, same is case u theta is gone, and here we keep it for the time being, because u z is non-zero. Then this we keep it, axisymmetry, this is gone. Okay. So, we have a reduced equation. So, you will see that is the reason we are discussing this case, because you will still feel that we are really at nonlinear equation. Okay. But one equation we did not use yet, that is not the theta component. If you see theta component, what you really get is complete left hand side is 0, right hand side viscous terms are 0, simply we get dou p dou theta is 0 from theta component. Okay. Nothing much. What is other equation that we have not used, which is equation of continuity. So, when you have unidirectional, what happens to the equation of continuity? For the time being, let us have this, we will revisit. So, let us go to the equation of continuity. So, that will be okay. So, now unidirectional. So, therefore, this is gone, this is gone, this implies u z is u z of r and theta at this stage, but we have an axisymmetry, this implies u z is okay. So, with this assumption, we would like to revisit our z component. Now, you see the nonlinear term, we have u z is function of r only, therefore, this term also goes off, then this term also goes off. What you are getting is, so this simplified linear equation we are getting. Okay. And we have dou p dou r 0 and dou p dou theta 0. So, immediate inference is P is function of z. Okay. So, this is the immediate inference, P is function of z. So, now the issue is we have dou p dou z. So, similar to the case of flow between parallel plates driven by a constant pressure gradient, you consider dou p dou z equal to some constant. So, then we can solve the corresponding linear ODE, right. So, let us see that all that we have discussed. U z is function of r, I have explained, r momentum, theta momentum, this is already discussed. Z momentum reduces to such a simple form. Now, you assume that pressure is constant, then this linear equation can be obtained. Okay. Now, when we are discussing about interior flows, this is a case of interior flow, right, because flow inside a pipe. So, when we are discussing about boundary conditions, in particular interior flows, we had a remark. What was that? The question to be asked is, are we allowing any source or sink in the interior flows? If you are not allowing, then you need a boundedness condition. Okay. So, as you can see, the solution is triggering a logarithmic singularity, right. So, what are the boundary conditions? No slip boundary condition on only one boundary, that is surface. So, U z is 0. Regularity condition, that is U z should be bounded at r equal to 0. This is required if you are not allowing singularities. If somebody is allowing singularities, so then corresponding source or sink has to be given. Okay. So, here we assume that there are no singularities inside the pipe, therefore, U z is bounded. Immediately to make U z bounded, we kill the coefficient A, that is 1, and r equal to A will be used to determine B. So, that is straightforward. As I indicated, boundedness condition gives you A is 0 and no slip gives you B, and we get this. Okay. So, the corresponding profile is also quadratic with radial distance. So, you get the corresponding profile. Okay. It is like this again. So, this is the profile. Why? Because the entire exterior is stationary. Okay. So, now let us see. So, this already we have discussed parabolic. Maximum velocity occurs at the center of the tube, okay, due to no shear at the center. So, that can be computed. Then average velocity. Okay. So, this is interesting. So, what we have taken? We have taken the corresponding surface element, integrated the velocity and normalized by the area of the corresponding cross section. Okay. So, that is what this is the average velocity. Okay. So, that means we have taken cross section and then we have computed. Okay. So, there is a relation, average velocity is half of u maximum. Okay. Then shear stress R z or z r is this. So, that is a linear relation with respect to the coordinate. Shear stress is having a linear relation with respect to the radial coordinate. Then shear stress at the wall. Okay. So, you may be wondering why repeatedly we are computing shear stress at the wall, etc. So, in most of the physical problems, these are a lot of applications. The interior also you can compute, there is no problem. Once you have a general expression, you have everywhere the shear stress, but why repeatedly we are computing on the boundary? So, these are the border cases where lot of physics happens. So, in most of the applications, you have to estimate something called a skin friction, that is the shear stress on the surface. So, this has a lot of importance. For example, if you are talking about flow inside arteries or thin endothelial glycocalyx. So, the shearing will if you increase the shearing, suppose you inject a drug and that is inducing lot of shearing, the tissue gets damaged. So, these kind of things can be estimated. Okay. So, that is the reason one has to estimate the corresponding the skin friction. Okay. So, that is what we are also computing. Coefficient of skin friction is the ratio of shear stress on the surface by the corresponding average velocity, okay, times the mass. Okay. So, this enjoys this relation. So, those who are interested in analyzing more depending on the skin friction, so we pay more attention, okay, and then analyze. So, with this you get an idea about simple geometries and what is the corresponding boundary condition, and then how the solutions can be obtained in exact sense. And that is the reason we are we stated this is exact solution of Navier-Stokes, but we have to take it with an assumption that these are for a simple configurations which ultimately are leading to linear ordinary differential equations, for which the theory is well developed, therefore, exact solution. Okay. So, once you have a nonlinear, then we have to go for various alternate techniques. Okay. Thank you.